Okay, is the screen visible, everybody?
Yes, sir.
Yes, sir.
Yes, sir.
Let us start with this one, that an is, we define the recurrence with respect to an, where the a1 is equal to 1. An is, it's a somewhat different kind of a recurrence, where you do not have only one single equation. You have an when n is odd, it is 2an minus 1. When n is even, it is 2an minus 1 plus 1 for all n greater than equal to 2. First of all, you need to make sure that you develop a single recurrence relation, not such kind of a different for odd and even relation, and then which can hold for both odd and even, a single relation, and then solve it for a closed form A. Just try out for a couple of minutes and then we will go. So you can see here that a1 is given as 1. So by this relation, you can find that a2, since 2 is an even number, I go by this way. So it will be 3, because 2a1 plus a1. A3, 3 is an odd number. I have to go by 2a2, which is 6. So this way the recurrence proceeds. These are some of the base terms. What shall you do?
So we can use -1 to the power n and model it. Like,
Yeah, one solution is like that. Then how it will look like? An is equal to
1 plus -1 to the power n by 2, like that. So means one part becomes 1 when n is odd, and the
yeah, I
other
can
one
understand.
becomes,
Then I mean, just complete it. I can understand what you are doing. Then
sir, whole upon 2, sir.
oh, it's a whole upon 2. Okay.
Into and so this term will become, when n is even, this will become 1. So we can multiply it by 2an minus 1 plus 1.
Yeah, or just you can do it this way. Isn't it?
Yes, sir. Yes, we can do this.
This will also do. Let me give you another solution. So from here, you know what to do, right? Because you have 1 and -1 to the power n, and an equal to 2an minus 1. You know how to go by the homogeneous part and the particular part and as well. Let me give you another simple version. If so, this equation, it is easy to figure out that this part has to cancel and this 2 will come. Some of the equations may be hard enough. So one of the things is that when you see even an odd division, try to do this and check if something goes common. Minus an minus 2, what will happen for even? What will happen for n equal to odd is this one, right? Yes or no? And for n equal to even, what will happen? Same this one, because 1 will cancel out. Agreed? So this we can do, or this we can do. Yes or no? Agreed, everybody?
Yes, sir. Yes, sir.
So now if from here you can also get a recurrence, because it's an minus 2 an minus 1 minus an minus 2 plus 2an minus 3 equal to 0. Now you know that how to solve these kinds of recurrence relations, because this is purely homogeneous. I mean, no particular part is there. So this is r cube minus 2r square characteristics equation minus r plus 2 is equal to 0. What are the roots? What are the roots? This is characteristics equation. What are the roots for this?
2 plus -1 and 2.
Plus 1 minus 1, 2. Now, do you get a feel that this will also do some kind of same kind of roots? It will move also in the same place, because when you go for the solution, you will have alpha into 1 to the power n plus beta into minus 1 to the power n plus gamma into 2 to the power n, right? And now you know that these are my basic base values, which I will substitute and solve for alpha, beta, and gamma, right? Yes or forgot?
Yes, sir.
Yeah,
Yes,
just
sir.
do it. I'm just not going with the calculation, but if you want to match at the end, you will see that your alpha will be 1/6, beta will be minus half, and gamma will be 5/6. So finally, you will get such kind of a thing. As a solution for n greater than equal to, let's say 1. Okay, I mean, eventually from here, you will come here by solving alpha, beta, and gamma, placing this base values. Here also, if you see the same way, if you try from this equation, what is the homogeneous part and what is the particular part, you will feel the same factor will come. See, 1 to the power n and minus 1 to the power n will come, as well as from the homogeneous part, some 2 to the power n will come. Agreed or not? Right? Homogeneous part will give some this kind of a thing, and the particular part will give this kind of a thing, and you know how to solve for the coefficients.
Yes, sir.
And you will again get same of the thing. So both is okay. I mean, but this is simple to figure out because this equation is simpler. Traditionally, for even odd, you look for such kind of options if you do not figure out by just looking into it as you have done here. Clear, everybody? A little different kind of recurrence, so I put it here. Okay, shall we move on?
Sir,
Yes.
Yes.
for solving an minus 2 is equal to 2 times an minus 1 minus an minus 3, we can put bn is equal to an minus 2. Then we will
Yes,
get
I
similar.
mean, see, solution is not the only the one way. This is the mechanical way, and we learned it, so I go by that way. Ultimately, you have to come in a closed form equation. That's it. You can go on expanding it. That is one of the options. Right? In some case, we have also seen that you do it in your way, but this is easier because if while doing or by expanding, if you mess it up, then your final answer will be wrong. But this is a way where it's less chance to mess up. Okay, that's it. Okay, let us move on. Look at this recurrence. An equal to an minus 1, n into n minus 1, an minus 2 plus n factorial for n greater than equal to 2 with these two as the base conditions. Try for a bit and tell me.
So we can divide by n factorial and then substitute an by n factorial as bn.
Great. So what we get if we divide by n factorial? Everybody just go this way. We are dividing by n factorial both sides. Right? Because n into n minus 1 cancels. Now what your friend is suggesting that let us put bn equal to an by n factorial. If we do that, if we put here this one, the same thing becomes bn equal to b of n minus 1, b of n minus 2 plus 1. Also, see where the mistakes happen usually when you do this one, you use this. Not you should use some other things, right? Your b0 and b1 should change also. What will be your b0? Here in this case it is 0 and b1 is in this case 1, but do not forget to transfer this as well while solving this. So the homogeneous part is nothing but Fibonacci, and you know for the one the particular solution how it look like. I give you a few minutes just to complete this one. Right? Homogeneous part is Fibonacci. You agree, right? Yes or no?
Yes, sir.
Yes.
Yeah. So from the homogeneous part, I'm just using my Fibonacci previous computation. And for the particular part, you get, let's say, beta into 1 to the power n, which is beta in fact. And when you have beta, how do you substitute here? You substitute in this, you substitute this in this equation by getting it beta equal to beta plus 1, which implies beta equal to -1. Right? So this is actually simpler because this to sum is the final solution. I have alpha 1, this to the power n, plus alpha 2, this to the power n, minus my beta, because particular solution beta is equal to -1. Now you know that if I put this b0 equal to 0 and b1 equal to 1 here, I can solve for alpha 1 and alpha 2. And finally, I will get a bn, but second source of error, you need to find an from here. So when you finally get a bn, transfer back to get the an by having an n factorial of the whole thing. Okay? Yes or no? Finally, I mean, if you just go on calculating, it is nothing but it is, we'll get this one. I take root 5 common, so the -1. Finally, we'll get this one, but I am not showing this to this part because this is simple algebra by putting the values and getting the values of alpha 1 and alpha 2 to finally substitute and get the answer. Okay. So 2 sources of mistake. I mean, I'm just putting it into the red. Do not forget to do this, and do not forget to convert it back. Clear, everybody? So this is some kind of substitution we make in terms of bn equal to an by n factorial and some arithmetic jugglery to make it a general record. Okay. Let me move on. A little bit tricky than the previous one. So it's a recurrence relation which says an equal to 2an minus 1 cube by an minus 2 square. A0 equal to 1, A1 equal to 1.
So we can substitute an by an minus 1 as bn then.
An by an minus 1 and then?
And then we can divide both sides by an minus 1.
Okay, so let's say let us go by my proposal was a little bit different, but let me start with your proposal first. You are doing it. I have this in my hand. What you are doing, you are also proposing that let me have an minus 1, right?
No, sir. Like this initial equation itself, we can divide by an minus 1 on both sides.
You want to divide the initial equation. So if we divide it by an minus 1, this is then
We take an by an minus 1 as bn, then we'll get bn is equal to 2 times bn minus 1 square.
bn equal to an by an minus 1. Then you are saying by substituting this, I will get bn equal to 2 times bn minus 1 square. Then
We can keep on recursively substituting till B1.
So this will be, this again will give 2 into 2 square into Bn minus 2 square. Like that you want to move on.
Yes.
So Bn minus 2.
Yeah. Go ahead then. I mean, where it will reach. What is B1 here? Let us go by, if B1 is A1 by A0, so it is 2, right? The base condition.
So it should be Bn minus 2 raised to power 4.
2
Yeah,
into
Bn
2.
minus, yeah, to the power 4. Okay. Then, I mean, what will be the closed form finally? Calculate and tell me. After going, where I will reach. So it is 2 to the power 1 plus 2. This is 4. Then 4. This is 8.
Yes, sir. 8.
How many? Up to?
So n minus 1 terms.
This will be n minus 1 term. So let me make it smaller. Sum I equal to 1 to n minus 1 2 to the power I. So what is it in the power?
So it is starting from 0. So
No, 2 to the power 1 to square, like this, na?
okay, sir. But sir,
Sir, at the end, B1 is equal to 2, so that also we need to multiply.
Yeah, so fine. At the end, B1 is equal to 2. So this one. No, sorry.
no, sir,
Not this.
B1
No,
will not be B1
no,
power 1. It's
no,
B1 power.
No, B1 power how much? That you need to multiply. Yeah, your friend is right, but I put it wrong place. 2 to the power how much?
2 to the power n.
N it is, or
2 to the power n minus 1.
no, but it is getting squared, right?
Sir, 2 to the power n minus 1.
Oh. Okay. Yeah, you are right. One of the lazy way is that take a log, na. What's the problem? Take a log base 2. Right?
Yes.
Now you know, like the previous one, I will now say Bn equal to log base 2an. This is my substitution, and this will give me B0 equal to, since this is 1, so B0 equal to 0, and B1 equal to, since this is 2, this is 1. Now if I do that, then my equation will be Bn equal to, this is 1 plus 3Bn minus 1 minus 2Bn minus 2. Now it is in your domain, right? Yes or no? Now it is in your domain, right? Characteristic equation is r square minus 3r plus 2 equal to 0. 2 roots, which is 1 and 2. And from this one, you need to consider this one in a different way because I got a 1 root. Remember, right? I'm not completing it. Homogeneous part will give you alpha into 1 to the power n plus beta into 2 to the power n. Particular part, since there is a 1 to the power n already there, so gamma into n into 1 to the power n. Correct?
Yes, sir.
So you know that this part first I need to substitute back here to get the value of gamma. Then upon getting gamma, I need to sum this up to get the value of Bn with this initial coefficient. I will go and solving it. चलेगा? हो जाएगा ना?
Yes,
Yes, sir.
Yeah.
Yes, sir.
And you will see, I mean, if my calculations or your calculations is correct, whatever you reach here, you will automatically reach here. Let me, and don't forget to substitute back. Okay. So whatever Bn you get, actually your An is equal to 2 to the power Bn. See here, This you do not forget. Okay, and if you do that, finally you will get this way. I mean, whatever we are doing here is perfectly okay. You see, this is this minus n minus 2. If you solve this one, you will get this. Okay, for all n greater than equal to 0. Okay, this is the final solution you will get after solving this. Particular, directly substitute, get back the gamma value. Take the full equation of Bn by Bn homogeneous plus Bn particular. Follow this base condition, solve for alpha beta, and then add those up. The whole equation 3, this 2 plus this, you will get Bn. Then do not forget to substitute back to An. Okay. All right. A little bit computer science oriented questions. Now tell me that if this be the code given to you or the function given to you, I make a recursive call with Fn. Okay. You need to give a recurrence for Fn and then a closed form telling me that how many x's will be printed. So it makes a print x, then it reduces the n, then it makes a loop by reducing m twice. The value that it gets initially, reducing twice and also calling the function again and again inside the loop. Just in a pen, take a pen and paper, just first see the set of recurrences it makes and try to figure out a recurrence relation for Fn.
Sir, two cases will be there for odd and even.
Great. Okay,
Sir,
so let us say.
in general, we can write.
Okay. Okay. Let me. I will go by your way only. Let me say that Ln be the number of x's for an n. Since you said two cases, I am giving you a big position. So one case is n is odd, right? And the other case is n is even. Okay, for all n greater than equal to 0 or greater than 0 anyway. Let's say greater than 0. Yeah, tell me now. What are the cases?
Sir, if n is odd, then it will be 1 plus sum over
Plus sum over
k is equal to 1 to n plus 1 by 2.
1 to n plus 1 by 2.
F of n.
Okay, so you are going by Fn. Okay?
L.
Okay. Okay, f of n
minus 2k plus 1. And in even case, the upper limit will change to n by 2 for this summation.
This internal part will be the same.
Yes.
Others, please check. Upper limit will be
n by 2.
okay. To ease your check, let us try to think in this way. See, suppose n is odd. If n is odd, then I have first x printed here while I come in. So if n is odd, 1 is printed. Then m becomes even. If n is odd, then m becomes even. For even m, I reduce, go back till it is 0. Right? Yes or no? Right? I go on calling it. Each call give me 1 excess. I go on calling it till it becomes less than 0. Till 0 I go. Then when it becomes -2, I do not go again. So therefore, I call it, let's say, 2k number of times. For example, if your m starts with 2k, then it will be 2k minus 2, 2k minus 4, and up to 0. Okay, so if I call it this many number of time, where my k can range from 0 up to, you see, n minus 1 by 2. Agreed or not? If your n is odd, if n is odd, this is odd. Yes or no?
Yes, sir.
Why n minus 1 by 2? Because I have started with n minus 1 and I reduce 2 at per steps. So I go till 0. So therefore n minus 1 by 2 reduce till 0. And I do it. Okay. Similarly, let me use a different color. When n is even, first x is printed here when I come in. This becomes odd. When this becomes odd, so every time I reduce by 2 and I go till 1, right? Because then I go till -1, I exit from the loop. So if n is even, suppose n is 17, I start with 17. Then I print an x, then come here, print another x, 15, another x, 13, another x, 11, and so on. So therefore, I can say it is L to k plus 1 because every time I am calling the m with the odd number, I started off with an even, that's why. And I go this many positions, right? N minus 2 by 2. This many positions from 0. Now check. See, if k equal to 0, m is 1. If k equal to 1, m is 3. Up to how much you will go? You will go n minus your n is even. So therefore, you go this many number of steps. Okay?
Yes, sir.
Yes? So that's your friend is trying to capture this one, but I just told you this way because I need to also verify whether these two matches or not. I mean, your friend is right in capturing this thing, but since it's a tricky algebra, we may miss something. So I make it simpler to see at least. So now you get such kind of an odd and even thing, and you know the trick, right? You know the trick how to go. How you will go here? See here -1 to the power n, apparently looking at it and doesn't work like that way, right? So the better way to go is
Difference of n and n minus 2.
2. Then what it results? Every time you see it results ln minus 1. Right? Because the last term will be there. So L2 into n minus 1 by 2 is n minus 1. Here also the last term will be there if I reduce it to -2. Isn't it?
Yes, sir.
Yes, sir.
So when you do this way, you know that what are the base conditions from the recurrence. What is your L0? What are the base conditions here? What is your L0 and what is your L1? If n is 0, then only 1. It doesn't go inside the while loop because n minus 1 is -1. So it doesn't go. If L is 1,
2.
Yeah, 2. So this is just like, you will see that this is just like your Fibonacci number, which starts with 1 and 2 instead of 0 and 1. So effectively, your ln is nothing but your Fibonacci number n plus 1. N plus 1th Fibonacci number. You solve it, you will get the same thing. You solve it by this. I'm just deriving the final thing, but you
So
solve it,
shouldn't
you will
it be
get
n plus 2?
Yes, sir. It should be n plus 2.
which one?
Sir, f n
Ln
plus 2.
equal to f
F of n plus 2.
ln equal to fn plus 2.
No, because L0 equal to F1. No, how do you start Fibonacci number? Okay, you are saying this way, right? This is F0, this is F1, this is F2. Yeah, ln plus 2. Okay.
And sir, here it is written that n is greater than 0. So should we start from L1 or should we start from L0?
Yeah, you can start from L1. If you start from L1, you see L2 equal to, I mean, you can start from L1, no problem.
Okay, sir.
Okay. Okay, but I mean, when you are here, I mean, the difficult part is this one. When you are here, it's your business now.
So then will it become fn plus 3?
Yeah. I mean, just check it. I mean, this better to put a gap. Check this position. But it is a Fibonacci sequence. It's finally, the recurrence. The beauty of this recurrence is that it's a Fibonacci sequence. The number of x's is a number of Fibonacci numbers. Clear, everybody? Those who has proposed this solution, please cross check here. I just have, due to the sake of the time, I am not going into your thing and this thing. Maybe you are correct. I'm just cross check. The concept that you made to do it is fine. Absolutely okay. Okay.
Okay, sir.
Good. Now some of the divide and conquer recurrences. This is a warm up to start. I think you can easily do it. Just go ahead and do it as we have done in the lectures. Okay, I forgot to mention the base condition here. The base condition is T1 is equal to 1. How do you ease this thing into a recurrence, simple recurrence nature?
N is 2 power k.
Yeah. Just before that, let us take a small jugglery. Just divide by n first. Yeah, then you are right. Just I will make n equal to 2 power k. If I assume that n equal to 2 power k, then obviously, and so this, and also, I mean, you can assume to make it more simple, sk equal to tn by n equal to t to the power k by 2 to the power k. So this reduces to sk equal to sk minus 1 plus 1 by k. Right? Yes or no? Agreed though. Just you need
Yes,
to
sir.
convert this one S1. What is S1? T1 by 1. Solve this one. What it comes. Just by expanding, you can do it.
Sir, S0 should be Tn by 1, right?
Yeah, S0. Yeah, S0 because you put this one first. Yeah. So this is how much it will go. So this. K minus 1, K minus 2, and so on. If you go, so this will be I equal to 1 to K plus your S0, which is 1. Okay. Now your the part that you often miss out is to go back till Tn, which is n into Sk. Right? Tn is n into Sk, so n into this full thing. And when you do that, you have to also substitute back your K value with this. So eventually it will come as n into 1 plus sum over I equal to 1 to K, which is log base n base 2, 1 by I. Okay. Do you know this harmonic series? It is the most closed form of this one.
Log.
Log.
No. I mean, do you know that how this harmonic series add on and go to Euler constants and all? Just search this one. I will not tell this. This is an harmonic series. So how does this harmonic series add up? Okay. So this way, finally, what we do is that we finally give a time complexity bound of the whole thing. And such kind of recurrence, only the constant part you have seen in merge sort, right? The constant part is different, but such kind of a reference where it divides by 2. Okay. You can complete, right? I am only giving the sketch because the rest of the thing is very mechanical. Only few things I have to put a note. That's what. The other way, you can also just expand this one and complete this. I mean, no need to substitute back always. I mean, you can start with this one and can say Tn by n equal to Tn by 2 by n by 2 plus 1 by log base 2n. Then again write Tn by 2 by n by 2 equal to Tn by 4 by n by 4 plus 1 by log base 2 n by 2. And in this way you do, then add all of them. So this cross terms cancel, this equal to add all of them. So finally you get Tn by n equal to somewhere it will come T1 by 1, right? Sorry, T2 by, so somewhere down the line it will be T2 by 2 equal to T1 by 1 plus 1 by log base 2. How much n by? It will be this will be just 2. Right?
Yes, sir.
So then it will be, so if this terms cancel, so only this term remains and this term remains and all the right side summation remains. So this is 1 plus this term is 1 plus all this sum, as you are seeing here. The same thing will come here. Right? So Tn is the same. This is also another way, just by expanding. Since this is simple, so we can directly view it. If it is a little complex, then it is better to go by substituting it and then have a simpler recurrence to view. Clear, everybody? So in your algorithms course, you must have gone through such kind of a recurrence, and you will, in your throughout your computer science algorithms, there are many cases where you have to solve such divide and conquer recurrences. Okay, chalega? Happy everybody?
Yes, sir.
Good.
Yes, sir.
A little different one. One of your friend has also sent a query on this. I mean, how to go with this kind of a recurrence. So I put this exercise also. So let's say I want to have in case of algorithms, usually we want such kind of asymptotic time complexity notions. So I want to have a theta notation. You remember, right? What is theta notation? I say Fn equal to theta of Gn when there are constants C1 and C2 such that C1 into Gn is sandwiching Fn with respect to this C2 into C1 and C1 into Gn, and C2 into Gn is just making it as a sandwich. Provided that for all n greater than equal to some constant. So if you have seen this, so this may be your C1 into Gn, this may be your C2 into Gn, and your function could behave something like this, but somewhere down the line it will be sandwiched. So this is C2 Gn, this is C1 Gn, and this is your function Fn. So why n greater than n0? I am telling it that, see, beyond a point like this, which is my n0, that means for large values of n, asymptotic behavior is that this will be sandwiched in this region, my function, upper bound and lower bounded by something. So that is the definition of theta. Now let us consider the first one. What we can make out from this? First of all, can you recognize that what kind of algorithm gives rise to this recurrence? I leave it as a thinking exercise. Just think what kind of algorithm you have studied, but not maybe this variant. So just think of how can we get this recurrence? But given this recurrence, how we solve, we will see here now. So the usual way to think of such problem is to build the recurrence tree. So what we do, see, every time when you have such kind of a recurrence, you try to solve it by solving sub-problems. And then your added up thing is this, the added work, every step. Now this also gives rise to something. This n is again divided as 2n by 3 and n by 3. So this is 2 square n by 3 square t 2 n by 3 square. This will give rise to t 2n by 3 square, and this will give rise to t n by 3 square. And here in both cases the added work is how much? 2n by 3 cases, 2n by 3 log 2n by 3. Here plus n by 3 log n by 3. Agreed? I am saying the added case here and the added case here. The added case here, because the recurrence goes like this with the additional here. Agreed, everybody? This will be my recurrence tree, right? I mean, I can move deeper. Yes or no?
Yes, sir.
Yes, sir.
Okay. See, I need to get a bound, right? I want to need to get a bound. Next observation, this is observation 1. So my observation 1 is that I am doing a work while splitting. Observation 2 is, look at this path. It is always dividing n by 3 and moving on. So isn't it this path will be the shallowest in terms of my depth? Yes or no? This path.
Yes, sir.
Will be the shallowest. This depth will be the lesser one, the least one. And look at this path. Isn't it this path will be the highest depth path when we finish up with something in the base condition? This path will give me the highest depth path. 2n by 3, 2n by 3, every time 2n by 3. Yes or no?
Yes, sir.
Everybody is with me? So therefore, in between, what will happen? I have this going on. Finally, I reach base here. Then somebody will go on like this here. Okay, this tree will go on like this, and here I find the final base. Okay, it may be like this kind of a truncated, I mean, this kind of a irregular shaped tree, but this is the least and this is the most. Agreed? So let us try to see. So if I cut the tree here, so my Tn must do more than this work, because I am removing this part of the tree already. So this part of the tree produces some additional work, right? If I say my time complexity of Tn is up to this much, so it is at least up to this much it has to be, because no tree leaf has finished here. Yes or no? If I only consider this much depth and conclude that whatever the work that I have done up to this much depth, if I sum them up, is my total time. So it is at least the total time that you take. Agreed?
Yes, sir.
So what is the depth here? Right? This depth is, every time we are dividing by 3, going into base, the depth will be like this. Yes or no?
Yes, sir.
Yes,
Sir,
sir.
could you please explain once?
See, this tree is a little bit tilted, right? Some branches finishes earlier, getting a T1 at the bottom. Some branches finishes late by getting a T1 at the bottom. Do you agree till this point?
Yes, sir.
Now, the least depth, if I cut the tree here and say that I will only consider this part of the tree in my total Tn. So this part of the tree, whatever be the additional work contributions from this part of the tree that I am circling, if we add this on, this will be at least this number, because this number is more than that. I am ignoring the lower part. Agreed?
Yes, sir.
So what is this height? This height is T1. If you can see that every branch here at every depth you get n log n. This is also bounded by n log n. If you sum up everything, you will see every depth is bounded by n log n. So the depth is log base 3n, and every depth is not giving me works more than this. So my Tn is bounded by this much. It should be more than that. Agreed or not?
Yes, sir.
Good. Now, since you got this part, the next part is simpler.
Sir,
Yeah.
sir, how are we saying that work is means at least n log base 2 of n at each level?
Because you see this level is n log base 2. This level, if you add on, it will be like this.
Means work is reducing, right? Total work.
Yeah.
At
Total
each.
work is reducing, but the thing is that
upper limit of work
no. This is greater than equal to. Look at this one. If it is less than this also, then this relation holds, no? See, you are saying my work is reducing from this depth to this depth. Okay.
Yes.
But I am saying if it does not reduce also, this is also greater than equal to. So if it reduces also, this will be greater than equal to relation will be there. No?
Okay, sir.
Okay. Same analogy. Now I will cut the tree at the lowest position.
Sir?
Yes.
So shouldn't it be less than? Because the maximum is n log n to the base 2.
No. Not the maximum is n log n. Every step produces n log n depending on its n. Why the maximum is n log n?
So means all steps are less than n log n. So Tn will be less than this.
There are this many steps. There are log n number of depths. So log n number of steps you have to add on. So this quantity, the quantity here, I term it as A. You are saying A is less than this. I have no problem in that. I am just only saying my Tn is more than that. If A is much lesser, then also Tn will be more than that.
But sir, we don't know if we multiply n log n with the number of levels, will it cross or not, right?
No. You know it. That convergence you will get it every layer. You know the convergence to get every layer. You'll get the convergence. See, it has a if you look at my lecture, it has a strict binomial coefficient running on. See, 2 square by 3 square, then 2 into this term plus this. Then in the bottom you will see NC0, NC1, NC2, and then NC3, 3C3. I have given a generic solution, T alpha n and this Have you seen the T alpha n and 1 minus alpha n in the lecture? You will see that this has a binomial, it produces a binomial number of these terms, and every time you sum it up, it will get reduced. So the worst it can go this. I am saying Tn should be at least more than this as well.
Sir, can we do like this instead? Like Tn is greater than 2 times Tn by 3 plus n log n raised to.
If you do that, you can do that. It is 2n log n by 3, I can do that, but that will not give you the tight always. Here, what I will do, see, now I will do the bound here also. And that will give me, from this part, the same analogy will give me, what is this depth? The longest depth. It is nothing but log this one, the longest depth. And if I assume that I produce this many works at every step, so it should be bounded by this. Yes or no? So effectively, see, I want to have a theta. So I am doing it in this way, not the exact. I am trying to get out the recurrence. So effectively, your Tn is n log n, and this is also, I mean, it's also a factor of log n. So it's n log square n. So I can say Tn equal to theta n log square n.
Sir, in the lower bound, we have taken the minimum height, but at each height, we are not adding n log n, and it is getting reduced.
No, I understand your thing. See, if you go on finding that how much you are adding till this height, then you will see you are adding this n log n plus n by 3 log n by 3 plus 2n by 3 log 2n by 3 plus so on. Every height you, this will contribute, this and this, you add on and do. But whatever you do, if this right side term, if I pessimistically take this also, then I have these many things extra to add. So it is at least of this quantity.
Sir, in this inequality, why are we writing greater than? Sir, we should write like equal to, right? N log n plus in the last one, sir. Bottom
This one.
No, so the one in
Or this.
orange. Yes, sir.
Yeah, one in orange. Yeah, I understand. One in orange. What you are saying is that this is equal.
Yes,
but
sir.
it is equal to. You should not go when you write equal to here. You could not stop it here, na? Then you have to add also this 5 trees. If you stop it here, then it is greater than equal to. Agreed?
So
If
we are
you
trying to
stop-
find the lower bound of Tn, right?
Yes, the lower bound is that if you stop here, cut it out, how many work you have done. So Tn must be at least this, because I do not consider this part. And Tn will be at most this.
Sir,
So what we are saying is that lower bound will be less than this one, sir. Log n into n log this.
No,
N log
what
n.
I'm saying is that this height, if I assume every step to be n log n, then this height Tn should be more than that.
Sir, we should assume something that should give a lower bound. We are assuming it to be greater than it.
Yeah, so Tn, this is, see, what is your Tn? If you cut the tree and do not consider the bottom branch, till this point, whatever you get, your Tn should be more than that, agreed or not?
Yes, sir.
That's why if you consider till this point, why I'm putting it greater than equal to, if you exactly add this one also, you will see this is a factor of C into N into log squaring. This is a factor of some C1. If you add this whole thing till this point, I am not going beyond this, till this point. Okay. This will be a factor of C into N into log squaring, C1 into N into log squaring. If you go till this point, the bottommost point, the right side bound, it will also be a factor of some another C2 constant into N into log squaring. And then I will say I am sandwiched between these two. So I get this.
Yes, sir. But sir, how did you get n log square n?
Because this and log n comes with log square n, because this is theta of log n. This is another theta of n log n. So theta of log n into theta of n log n. See, log base 3 by 2 n is less than equal to some c1 into log base 2n. You agree?
Sir, it should be greater than equal to.
Which one?
Log base 3 by 2 of n should be greater than equal to c1 times log base 2 of
No,
n.
no, no. I am saying that the greater than equal to is also a relation, but can you say this? Just tell me, can you say this or not?
Yes.
Both sides,
Yes,
then
sir.
it should hold. Both sides, then it should hold as per definition.
Sir, can you explain the lower bound once again? Means how are we getting it? I still did not understand.
You just expand the tree. You just add up these terms. Then to you're fine, right? Forget my way. Forget my way. Forget this one. You expand the tree till this point, till the log n depth, n base 3 depth, right? You add this, all the works. Okay?
Okay, sir.
If you add all these works, I claim that you will get an equation where this will hold. This will hold for a constant C1. That's my claim.
Oh,
Okay. Similarly,
Sir?
for the
Sir, for determining the bound, you are multiplying the first height to its the number of operation done in the height, right?
forget all this. You just add on, as I told the last week. Forget all this. You want exact thing, you add on and proceed. My claim is if you add on and proceed and get a closed form, you will see your Tn will be greater than equal to some constant into n log square n.
Yes, sir.
Okay. Similarly, for the higher bound, you add on and you will see there will be some constant C2 into n log square and it will be less than equal. Therefore, I conclude this theta. Forget about my approximation about n log n. Do not approximate. You do exact and see what happens. Okay. The final one, I just quickly give you a hint that every time you are throwing n by 10, you see here, Tn by 5, when it get branch out, then the added term is plus n by 5. When this get branched out, the added term is plus 7n by 10. So first level is n, second level you are throwing 1 by 10, right? When you add up, you are throwing 1 by 10th elements. Yes or no?
Yes, sir.
Tn is Tn by 5, T7n by 10. The added thing is plus n here. Here, when you go by Tn by 5 square, this is 7n by 10. So 7 by 10 into n by 5. Here you are adding plus n by 5. Here, when you do, you are adding plus 7n by 10. So if you add up now, what is your Tn? If you add up now all these things, it is n plus n minus n by 10. Okay, every time 1 by 10th n you are throwing. So this is n minus n by 10 square and so on. Agreed?
Yes, sir.
Yeah. Now you know how to do it and bound it, and finally, the same way as we followed earlier, you bound it using this. What is the second equation? This equation, where do you find? Have you found this in your algorithm course? Median finding, is it studied? No, na? Median? Yes or no?
No, sir.
Okay. There is a very famous algorithm, this median finding. if you can go by that, median finding can be done in order of n. I mean theta of n. That's the whole point. Try to find the median of n numbers and then see this algorithm. The best known algorithm runs in theta of n. Okay, I stop here so that we could take over the.
Excuse me.
Yeah, please.
Here Tn should be n plus n minus n by 10 plus n minus n by 10 minus n by 10 square.
N by 10 square. Yeah, this way. Right?
No, sir. N minus n by 10 minus n by 10 square.
Why you are saying so? It should be this way. No? You just go ahead. I mean, this arithmetic. It should be this way. Every time this chunk gets out.
Yes. Okay.
It should be this way. Okay, I'm stopping here. So let Professor AD take over. Yeah, there is only one comment. Yeah, taking log. Yes, Sivansh, I missed it. Yes, you are correct. Okay, Professor AD, I am stopping here.
Yeah, I will start, but I suggest that we have some couple of minutes break. Is it okay?
Hello, sir. Will we get lectures this week or not, sir?
Yes.
Yeah, final set. I mean, one part is only remaining. Groups.
Okay, sir.
Only one part. Groups remaining. 2 lectures possibly we will upload. And maybe if you are interested, we shall upload applications of this algebraic structure. But that's only for your interest. The theory part is up to groups or coverages.
Yeah, so that is actually an issue. So maybe a small tutorial on groups is okay. So shall we wait until next Monday, which is the day before
exam?
Yeah, before the final test.
One thing we could do is that since this group we will have a small thing, we can just upload some of the solution questions and give them a quick tutorial so that if they have any query, we can solve it through mails and all.
What I'm suggesting, of course, they will have to go through this, right? Yeah. So Thursday will be a little bit too early.
Yes, that's what.
That's also
maybe a small tutorial on group we will put up so that let them go through that. Some solve solutions as well.
Yeah. Anyway, fine. Let us see. No, Thursday will be a little bit too early.
Yeah, and Monday will be too close to the exam. That's what.
Yes. So
I think let them go by their own pace. We will just upload some solutions.
Okay. So I think it's already 11:12. Maybe I will start. Anyway, I will give you explicit solutions to these exercises meant for today. But since I do not have enough time, so I will be a little bit sketchy. So you figure out all the detail. Okay. Okay, so I start by yes. So is it visible?
Yes, sir.
Okay. Okay. Okay, so to start with, I will just mention that I have an unusual query, not technical really, about this algebraic structures. So somebody asked whether why the subtitles in YouTube are in German. Well, I don't know. I didn't generate it.
No. I think you can change it for the subtitle your language.
Oh, I think this is auto-generated.
Okay.
So I don't know. I didn't add any subtitle or anything like that. Why it generated in German, I do not know. I will check whether the German makes any sense or not.
Better to put off right now while listening.
Yeah, so I will just check if it makes sense or not. But anyway, I didn't do anything. This is auto-generated. Anyway, so okay. Anyway, so rings and fields. I will just brush off a few important concepts. So you have seen in the video that if I define the operations with u equal to -1 and v equal to -1, then I see that all the ring axioms are satisfied. Okay. So instead of -1 and -1 here, let us ask a little bit general question. So if I put something like u here and I define addition of two integers this way, a plus b plus u, where u is a constant. And if I define multiplication this way, a plus b plus vab, where v is again a constant. So I want to find out for which values of u and v, this gives me a group on the set of integers. Okay, which gives, for which values of this u and v, I get a ring, not group, ring. Okay, so just let me recall, if I need to have a group, maybe I can switch this. If I want to have a ring, what do I have to have? So with respect to plus, what are the operations? First, closure. Second, associativity. Third, additive identity. And finally, additive inverse. Whereas for the product, I should have closure. And it should be associative. This is the basic requirement. And then I have the distributive laws. Of this over this, of this over this. Okay. So if I define addition and multiplication this way, let us see what closure, associativity, identity, inverse, and all these things essentially imply, but what conditions they impose on u and v so that all these axioms are satisfied. So closure is first of all obvious because you are doing u and v are given to be integers. So a plus b plus u is an integer, a plus b plus vab is also an integer. So this is obvious. This closure is also obvious. Okay. I should also have commutativity here, right? Addition is commutative. Commutativity is obvious because this is symmetric about A and B. So this is also fine. Okay. So associativity, can you please check? Does it impose any restriction on U and
No,
V?
sir, it's also fine.
Okay, associativity holds for any value of U. Likewise, if I look at the associativity of this multiplication, what happens? Does it impose any restriction? The simple matter to check. Maybe I will just write this. This is A plus B, B plus VAB, C, A plus B plus VAB plus C plus V, VAB times C, right? And this simplifies to A plus B plus C plus V. If I take common, AB, AC, BC, and then I have V square ABC. Then you also work out this quantity. What is this?
So same.
It will be the same. Okay, so we just work it out. So this is also fine. This also does not require any constraint on U and V. Now, what about identity? Additive identity.
So minus U.
Minus U. Okay, so you check. Additive identity is minus U. Again, whatever U is, this is fine, no problem. What about this inverse? Inverse of A?
Minus 2U minus A.
Okay, good. So inverse of A is minus 2U minus A. Still, we do not see any constraint on U or V. So the only, I would say, thing that requires some constraint on U and V will be this distributive loss. Okay, you can also see that this multiplication is commutative. So it's a commutative ring because it's symmetric about A and B. A plus B plus VAB is the same as B plus A plus VBA. Although for a general ring, I do not require commutativity, but in this case it happens. So it is sufficient to check only one distributive law. So can you work it out? If I have something like this, A.
Sir, I got UV equals to 1.
What UV equals 1? Just work it out. Okay, then you require constraint UV equal to 1. Okay, so this is just manual calculation. I am not doing it in order to save time. I do not have sufficient time. So what restriction do you have now on U and V?
So both should be +1 or both should be -1.
So the only two possibilities, since UV are integers. So one possibility is U equal to V equal to 1, whereas the second possibility is U equal to V equal to -1. Only for these two pairs, 1, 1 and -1, -1, this will give me a ring structure. Okay. Okay, so this calculation is a little bit, I would say, involved. Not much. For you, it is nothing anyway. So this is fine, right? This exercise is essentially given so that we can brush up concepts of rings. Basic definition. Okay, so it turns out that this is also commutative. So it's a commutative ring. This is also quite straightforward. So next, let us look at. We covered this -1 thing, right? A plus B minus U and A plus B minus VAB. Sorry, A plus B -1 and A plus B minus AB. So let us work something on this U equal to V equal to +1 thing. Okay. So you just take U equal to V equal to +1. Okay, so what you are supposed to do before doing this, first show that this is a commutative ring with identity. Then Z is a commutative ring. Of course, commutativity is obvious. With identity or unity, whatever. Some people call identity, some people call unity. So what is the identity? Multiplicative identity?
Sir, 0.
0, right? So okay, so all these things you can clearly work out. For example, if I take A dot 0, A plus 0 plus A times 1 times A times 0, which is A. Okay, likewise 0 dot A is also A. Okay, anyway, it's commutative, so it suffices to look at only one of these two things. So multiplicative identity is 0. Next question is that find the units of this and their respective inverses. So what is a unit?
Elements having a multiplicative inverse.
Element having a multiplicative inverse. Okay. So these are called units. For example, in this original plus and dot, I mean normal integer addition and multiplication, the units are 1 and -1. These are only invertible things. With respect to this structure, what are the units?
Minus A by 1 plus A.
Minus
A by 1 plus A.
So 0 and -2.
0 and -2, yes. But why did you say minus? Okay, let me work this out. Suppose that A multiplied by B with respect to this definition of multiplication gives me the identity. And this should be 0, not 1, because 0 is the multiplicative identity. Okay. So this means I can find an integer B for a given A such that now V is equal to +1. So this becomes equal to the multiplicative identity, which is 0. So if I write B in terms of A, what is this? Minus A over A plus 1, right?
Yes, sir.
Okay. Now this has to be an integer. Otherwise, A cannot have a multiplicative inverse with respect to this multiplication. So what are the possibilities for A? This must be an integer. So the only possibilities are A equal to 0, minus 0 by 1, that is 0. And what about another possibility is -2, right? -2 minus -2 is +2, -2 plus 1 is -1. So only possibilities are this. And if A is 0, what is B? This is also 0. And if A is -2, B is again -2. So these are inverses of one another, I mean each other. -2 is the inverse of itself, 0 is the inverse of itself. Happy or not?
Yes, sir.
Okay, so this is just for brushing up the concept of units. Okay, so next about again recollecting or recapitulating the concept of subrings. Prove that the set of all odd integers is a subring of this ring. Then we will look at the set of all even integers. What is a subring? Somebody please tell.
Sir, a subset of the original ring which satisfies the conditions.
Satisfies all the conditions, and we have seen that the only two conditions that we need to check is that given any A and B in that subset, A minus B should be there, and the product AB should be there. Okay. So, yeah. So, suffices to check that A and B odd implies A minus B and A multiplied by B are also odd. Then you have the closure under subtraction and under multiplication. And only these two things you need to check. You do not need to verify all the 7, 8, 9 ring axioms one by one. Okay.
Sir.
Yeah, tell.
Sir, for ring we have defined only two operations, plus and dot. So minus is like
this
A
is the
plus
inverse
minus.
operation. Yes. So it's basically this is basically A plus minus B. Only thing is that this is not equal to minus B as an integer.
Additive inverse.
Yeah, this is the inverse. Inverse with respect to this. Okay, so it is not equal to minus B as integer. What is this?
Like B circle plus of minus B is equal to 0.
So you see, what is the additive inverse? Minus 2u minus A. And now I am taking u equal to 1. So minus 2 minus B. So this is nothing but this quantity is A minus 2 minus B. Agree? This is inverse one with respect to our conventional addition. Okay. And then what is this? This is A plus minus 2 minus B plus, because you have taken, I have taken u equal to 1.
Sir, plus 1, right?
Sorry, this is not multiplication. Sorry. Yes. This is not multiplication. This is addition. Plus 1. So this is what? A minus B minus 1. So this is odd, right? If A and B are odd minus odd is even, even minus 1 is odd. Agree or not? So this is odd. And what about this? A plus B plus AD. Okay. This is odd. This is odd. Product of two odd numbers is also odd. So 3 odd numbers, if you add up, you will get an odd number. So this is also odd. Therefore, under these two operations, multiplication, subtraction, which is basically addition with the inverse, and this, the odd numbers are closed, and therefore the set of all odd integers for is a subring. What about even integers?
No, sir.
Right.
The additive under the subtraction, it won't come under even.
Okay. If you look at this, it is, if it is A and B are even, even minus even is even, minus 1 is odd. So it's not closed. Okay. In fact, you can see even this is not closed. In fact, anything should fail, not necessarily subtraction. I can just also look at this. A plus B plus AB. 1. Sorry, 1. So this is even, this is even, this is even, this is even, this is odd. So even closer does not hold for this or this, whatever, doesn't matter. Okay. So the even integers do not form a subring. Odd integers do. Happy or not?
Yes, sir.
Yes, sir.
Okay, good. So
Sir,
third, yes, tell.
sir, you said that in the subring it shall contain 0. So
What is the 0 here?
additive identity.
What is the additive identity? This is minus u.
Okay, yes.
This is minus 1. Minus 1 is odd. Anyway, that way also you can just argue. Even numbers do not contain the additive identity. It cannot be a ring. Yeah, there are many ways of proving this part. No problem. Okay. Next one is about homomorphism or isomorphism. So we have two possibilities, right? U equal to V equal to 1. Let us call this ring Z1. And we can also define U equal to V equal to minus 1. Or you can take U equal to V equal to minus 1, and still we have a same ring, Z2. Of course, this Z1 and Z2 are on the same set, but with different operations. So here A plus B plus 1, and here A plus B minus 1. A plus B plus AB, A plus B minus AB. So you find out a ring isomorphism from Z1 to Z2. Okay, so let me once again write. So if F is a ring isomorphism, what it should be is that for any AB I take in Z, because the underlying set is Z, I should have F of add, but this time you are adding in ring 1. And then if you add, you should have this. Likewise, F, A, multiply and then apply F, you will get the same thing. You apply F and then multiply. That's by definition of homomorphism. Moreover, I want F to be an isomorphism. So in addition to, so this is the general homomorphism formula. Now, since we are having an isomorphic, this should be a bijective map. Okay. So can you propose something?
Sir, A equals A to map A to minus A.
Okay, right. So I can take FA equal to minus a for all a in Z, and clearly this is a bijection. Now what I have to verify, what is f of a plus 1b? This will be f of, sorry, okay, fine. What is this? A plus b plus 1. Happy? Because that is in this ring, u equal to v equal to 1, so this is plus 1. And this f will map it to minus a plus b plus 1, which is minus a minus b minus 1. This is nothing but minus a. I am adding with respect to second group, second ring operation. This, but this is fa. This is fb. Okay. And likewise for multiplication, this will be f of a plus b plus ab minus a plus b plus ab equal to minus a minus b minus ab. I can write it this way, minus a minus b minus a minus b. So this is nothing but minus a multiplied with respect to the second operation, and this is this. Okay. So this is a ring isomorphism. In fact, a ring homomorphism, and clearly this is a bijective map. Happy?
Yes, sir.
Okay, good. So this exercises are just for brushing up the basic concepts. So now let us do a little bit more on the application side. So let R be a commutative ring with identity, and Rx, the set of all univariate polynomials with coefficients from R. For example, we may consider R as Z integers, and this is the set of all integer valued polynomials. And you know how to add and multiply polynomials, because that addition just requires coefficient by coefficient addition borrowed from this mother ring. And multiplication is kind of convolution, right? Convolution involves multiplication and addition. Okay. So these two operations are inherited from R. So this is the famous polynomial ring. So prove that this is a ring. So you have to find out all the, you have to, I would say, verify that all the ring axioms are satisfied. So I think this is pretty straightforward, part A. Addition, straightforward, right? Closure is obvious. Multiplication, associativity is obvious, because this is borrowed from this R itself. Commutativity is fine, because R is assumed to be commutative. Okay. So I leave this part A to you. A, straightforward, check. So let us look at this part B. Prove that this is an integral domain if and only if R is an integral domain. So can you tell me what an integral domain is? So you give me the definition.
So A dot B equals to 0 where both of them are not equal to 0.
This thing should not happen, right?
Yes, sir.
Okay. So first of all, it should be a commutative ring with identity. So Rx is also a commutative ring. That is fine. In fact, it also has an identity. This is the same identity, the constant polynomial. Okay. So it should be an integral domain if and only if you cannot multiply two non-zero elements and get the zero element. Okay, so that is the definition of integral domains. Okay. So let us try to prove this. First, this part. Assume that this is an integral domain. So Rx is a domain. Okay, some people actually shorten this integral domain as just domain, but anyway, let us use integral domain. Then how do you prove that R is also an integral domain?
We only consider polynomials of degree 1.
Degree 0.
Yes, sir. Degree 0, sir.
Okay. So R is canonically contained in Rx. Right. So this is basically the constant polynomials. And since this is an integral domain, the question does not arise that you multiply two non-zero constant polynomials and get the zero polynomial. Impossible, right? Therefore, R is also an integral domain. What about this?
Sir, we can assume that for two polynomials which are both non-zero, we get the zero polynomial as a result of the multiplication, and then we arrive at a contradiction.
Okay. Okay. So this is also fairly straightforward, just a matter of checking. Assume that Rx is not an integral domain. That means by definition, I have two non-zero polynomials, Ax, let's say. This is non-zero. And Bx, some other degree. This is also non-zero. And I choose these degrees d and e in such a way that AD is not equal to 0. BE is not equal to 0. Okay, this is how I define degree, right? Then what should I do?
Sir, we check the coefficient of x to the power d plus e in the multiplied polynomial.
So Ax Bx is equal to 0. So this implies all coefficients are 0. So coefficient of x power d plus e, which is equal to AD times BE, this has to be 0. And this is a non-zero element. This is a non-zero element. Multiply them. I'm getting 0. So this implies R is not an integral domain. Okay. Happy or not?
Sir, can we take some other coefficients of power of x?
Other coefficient means?
A constant.
I can have A0 equal to 0, B0 equal to 0, or one of them may be 0. Because, for example, x square plus 2x is a polynomial, right?
Yes, sir.
Okay. But I am taking this as non-zero because this defines the degree of the polynomial. It has to be non-zero. All other terms may be 0. Okay. Similarly for dx.
Okay, sir.
Okay.
Sir,
Yeah, tell.
sir, while defining degree of polynomial, AD not equal to 0, right? But this 0 is the constant 0 integer.
Not, I mean, the 0 of this R.
How means if it is a polynomial, if we forget it is a ring, if we just define it as a polynomial of degree d, then the coefficient of x power d must be non-zero, right? But
that is how we define degree, right?
yes, but this 0 is a constant number and the AD into BE equal to 0. This 0 belongs to the 0 of R. So how can we say that 0 of R is same as 0? Like,
Oh, so that part is written here. You just check what is the 0 of this. What is the 0 polynomial? It is basically same as the 0 element of this ring. Yeah, of course. These two zeros are basically the same.
oh, means that we have proved in the first part, right?
Yeah,
Means
actually we skipped it, but you just check what is the 0 polynomial. It is basically that same element as this.
Okay, sir.
Same 0 as this. Yeah. Okay, understood your query. Is that fine? Then I think I have just time for one more. Which one is, I have to, maybe let me do this thing first. Then I will go back to that if time permits. Okay, so what I say, I just look at all real numbers of the form a plus b square root 5, where a and b are integers. This is an integral domain. Once again, this part, this is a straightforward check. And if instead of taking integers, if I take rational numbers, these combinations a plus b root 5, they turn out to be a field. Every non-zero element is invertible, so that is the big question. So this is also fairly straightforward to check. In fact, why? These are all subsets of the set of real numbers, which is a ring, commutative ring with identity, actually. So all you need to check is that this is closed under subtraction and multiplication. Yes or no?
Yes, sir.
Okay, so I take a plus b root 5, c plus d root 5, multiply and subtract. You will see that they are also of the same form. Here also. Commutativity is borrowed from R itself. Okay, if I work on a subset of real numbers, suddenly my multiplication or addition cannot become non-commutative. That's impossible, right? Anyway, so this is a fairly straightforward assertions to check. Part C is the interesting thing. Argue that this contains infinitely many units. So far we have seen several examples like Z under traditional addition, subtraction, addition and multiplication, or that kind of thing that we dealt with in first 3 exercises. There we had only 2 units. Okay. So traditionally plus minus 1, and there we have found some 1 or minus or 0 or minus 2 or something like that. Okay. On the other hand, if I take a field, every non-zero element is a unit, right? Here you can see that everything is not a unit. Also, there are many units, in fact, infinitely many units. So many such things may happen in a general group ring. So how do you establish part C? So 1 and -1 are units here also, no problem. 1 is of the form 1 plus 0 times root 5. -1 is of the form -1 plus 0 times root 5. So these are anyway units. But there are other units.
Sir, minus 2 minus root 5 is a unit.
Minus? Yeah, tell us just once more.
Minus
So minus 2 and
root
1.
5.
-2 plus root 5. Okay. What is its inverse? Sorry, multiplicative inverse?
No, sir. Minus 2 minus root 5.
Minus root 5, okay. Well, if that is a unit, 2 plus root 5 is also a unit. Anyway, let me just clean this part. Okay, so 2 plus root 5 is also a unit. If minus of that is a unit, so what is the multiplicative inverse of this?
-2 plus root.
-2 plus root 5, yes. So you have at least identified one unit other than plus minus 1.
So now we can raise it to any power.
Okay, good. So if I raise it to any power, I will continue to have 1. For all n greater than equal to 1. Now, why will this give me different things?
Sir, why n needs to be greater than 1? Why n needs to be greater than 1? Okay, sir.
This is equal to 1, yes. So why we will keep on getting different things? Because
the magnitude of 2 plus root 5 is greater than 1, so it will like 2 plus root 5 to the power n will be strictly larger than 2 plus root 5 to the power n minus 1.
Yeah. So they will get it. I mean, we will get an increasing sequence, increasing sequence of increasing values, larger and larger values, and they cannot be equal. So these are all different. Okay, from one another. So it contains infinitely many units. Okay, so this kind of rings are called number rings. Okay, so this kind of rings are called number rings. Although this looks like a bit too much mathematical, it is, no problem. But if you study something like factoring large integers, currently the best known algorithm is called the number field sieve method. And these number fields are nothing but this kind of number fields or number rings. Okay. So this is a very sophisticated algorithm, but possibly I can give you a feeling why we are studying this kind of algebraic structures. For solving some computational problem, we require things like these number rings and number fields. Okay, these are actually quadratic number fields or number rings because square root 5 is a quadratic thing. And number fields, we usually work with degree 3 to 5 or 7, something like that, that kind of number fields. Anyway, but you see an application at least. However abstract these things sound, we still have applications. Okay, so.
Sir?
Yeah, tell. Yeah.
Sir, in this example, sir, how we got the first unit?
Actually, this mathematics is a little bit too complicated for you to understand at this point. This is what is called a fundamental unit. Okay, and there is a theorem on units about this number rings, Dirichlet's theorem of units. Okay, let us keep this for later. I mean, in a later course, if you really are interested in number rings, you will come across such things. So what is a fundamental unit and what is that unit theorem? Here it's just, I would say, just by some kind of search.
Sir, but without knowing the theorem, sir, how can we prove that it contains infinitely many units?
How can you prove? Okay. Because I told that it contains infinitely many units. Okay. So you have to find one and give some argument. And finding the first one, this is basically, not really that difficult, right? Because if you have something like this, this is equal to 1. Now this is actually something that is where this root 5 is not involved. Okay. So somehow you have to cancel this root 5. So the basic intuition is that this should be of the form a minus b root 5. Okay. Yeah, this is a good idea. So I am essentially looking for, integer solutions of this so-called Diophantine equation, a square minus 5b square equal to 1. Okay, or minus 1, whatever. Actually, we have found minus 1. So that is the idea.
Okay, sir.
Okay, that is how you get it. You do not need any sophisticated, I would say, theorem on units and all that stuff. Okay, so this is the idea. So this may be 1 or minus 1, whatever, plus minus 1. Okay, solve this and you get the first example. Okay. So this is an interesting thing. If we have fields and a non-zero ring homomorphism, then 1 maps to 1 and this has to be injective. I would upload a solution of this. It will take some 10-15 minutes time maybe. So I will upload a solution. You just read that solution. And there will be too many exercises in that exercise set. This is just for the sake of our compilation. Actually, in 2019, we covered this groups, rings, fields, and all this stuff in algebraic structures in a, I would say, much bigger detail than we are doing this time. So at that point of time, we compiled many exercises. But anyway, we will find a few exercises. If you have time, solve a few of them, 5 of them maybe. That's good enough. Yeah, so I think we stop here. And of course, don't forget that next week we are having our test 3. Okay. Okay, so any questions for the moment?
Sir, when will be the next tutorial class for the new videos we get this week?
Yeah, I will upload today. I will upload. Okay.
No, I mean the last week, whatever you have done, this tutorial is complete, so we will upload that. So this week's, if you ask that, we will have some problems with solutions. You go through it. Since we are covering it in the last week, we expect less coverage on that. But the basic coverages we will try to produce with a tutorial that helps you. Okay, as Professor Reddy was saying, in 2019, when there was a live class, we had a much, long period to cover this group ring and field. So we went into much deeper. So some of the exercise may be a little bit involved. So you practice the basic ones and the covered ones. I hope you can answer such questions in exams also.
In fact, most of the basic definitions and all these things are brushed up here, right? That is the way we have chosen this particular subset of exercises. Anyway, let us stop. So today I will upload these 2 extra videos, and I would say an extra two last videos and 1 extra thing. It's just an applications to cryptography and things like that. And I will upload 2, this exercise set, and also the last week's thing, recurrence relations. Okay, so that's the plan. Okay, so any queries for the moment? Okay, I think I should stop presenting. Okay, fine. So if there are no queries, let us call it a day.
Thank you, sir.
Thank you, sir.
Thank you. Thanks for joining.
Thank you, sir.
Okay. See you next week.
Thank you, sir.